Okay, so let's start. So I'll talk about robustness, but I just want to mention two slides from the lab, just to tell you where I'm coming from. So last year we had a bit of a blast in terms of stories. So we've identified a new cell cycle step here, the radial step where the microtubules are becoming radial a few hours before the preprophase band formation. And we think this is the step where the cell is sensing its own geometry. We've also identified the boundary of the shoot apical meristem, a zone where the blue dots here, this is where the water is going away. And so the cells are shrinking, and this is because the organ is draining the boundary. So when we look at the molecular signature here, we can see a drought. So if you looked at the transcriptome of those cells, you would think that this plant is drying, basically. So we think that water can be, in the Turing sense, called the amorphogen. And we also found a new floral structure that we call the floral lock. So it's very early on, it's stress-derived bending of the tip of the sepal, and this locks the bud for a while. And the latest thing that we are quite excited about is this protoplast story. So we found that some protoplasts make very long phylopods like this. So you just digest the protoplast, and 20 to 30% of them are making this. It's been somewhat not really seen before, but actually we think it's super interesting because it looks a lot like a fibroblast, but not an active fibroblast, it's sort of passive fibroblast. This has a lot of resonance with the Etienne strands, for instance, and adhesion to the cell wall. But I'm not going to talk about all this because of that. So this is what you see here is rock. It's about 1,000 tons. And we know that this rock has been moved by a storm or several storms about 120,000 years ago. And this was the last time it was +2 degrees Celsius global temperature compared to pre-industrial times. So when we have huge hurricanes here now, it's 100 tons that is moved. So now it's 1,000 tons. So what we're going to see in the 21st century and also in the 22nd century, probably the 23rd century, is a very fluctuating world, lots of turbulence. And this is the #1 message from IPCC and all these reports. It's going to be much, much more variable than anything we've seen before. So based on that, there's a number of reflections we can think about. Of course, with some the Meadows report that is a classic in the sense. Here you can see the company, let's say. And so there's one thing that I'd like to insist on. So this is the scenario in the old style from the 70s. Of course, now there's better drawing of this, but I like to show the original drawing. That shows basically when you look at the prospect from 1972, it's a bell-shaped curve for pretty much everything. And we are exactly at the point of the turning point. And when we look at the factors, at the parameters of socioeconomic parameters, you can tell that we are actually in the tipping point right now. So for instance, the life expectancy in good health in the US has been increasing until 2012. It's decreasing since 2012. So this is a bell-shaped curve applied to health in the US. But there are many, like the debts in France, right? When you have more than 3,000 billion euros in debt, that means that it's degrowth, already 4 years. So that's the scenario, so bell shape. So that means that it's present time. It's not something that we are forcing for the future. It's happening now in many places in the world. And so for this, we often think that we are going to get more resources. So, deep sea mining, all these things. So, in 1972, they did the scenario. So the scenario is the following. So if you have some magic access to resources, what you get is exactly the same curve, but more pollution. So I wish some stakeholders would see this model from the 1970s. It's completely useless to look for more resources. Okay, and so this comes down to systems thinking, and this is the quote from the Meadows report: running the same system harder or faster will not change the trajectory as long as the structure is not revised. So that means that we can add a lot of new solutions to a system that is in a deadly trajectory. It's not going to change the trajectory. We are just going to go faster or slower into the same objective. We need to change our objective. Okay, so of course, I'm going to land on the plant subject, and don't worry. Okay, so what does that mean for us, research in agriculture? So what we see in research and agriculture, as in any field, is that when the situation is becoming more and more urgent, what we do is that we increase efficiency. The word efficiency has been pronounced a few times today already. performance, efficiency, efficacy. I mean, we want to accelerate in a world that is going to experience a lot more fluctuations. So this will most likely keep us on exactly the same trajectory. We're just going to go faster on the highway. Maybe we need to exit the highway. That's more like what I want to say. Okay, so what can we say for this? So if we increase performance, efficacy, efficiency, for instance, we have many examples in society where we can see that when we increase efficiency, it has actually some negative effects. So this is the Suez Canal, you know, like that's an optimization tool. When you optimize maritime transport, actually now you're very sensitive, you're very dependent on a tool for everything, right? For medicine, for all stuff. And then now you're blocked. And some companies, they take several months to recover from this. But we have exactly the same thing in research. So just go for the editing. So if you make a very performant crop, then farmers will be dependent on that crop. And when it's sick, what do you do, right? So it's the same type of idea. So that's why diversity should be the priority over the efficiency of the crop. Rebound effect. So that's my famous example for the fridge. So the fridge, they were not very energy efficient in the 60s. We've increased the efficiency of the fridges. Now they're very sober, right? They don't consume so much energy. But what happens? We multiply them, we make them bigger, we make smart fridges, we have wine cellar, and now the population of fridges is consuming more energy. So we want to be more efficient in terms of energy, but actually we are less efficient. We actually consume even more energy. It's the same for plant research. So a classic example is the work from Rob Martinson, for instance. If you read his papers from the 2010 to the 2015, exactly when we had the entire, or not the entire Sumatra almost, that was deforested to plant palm oil. And Rob Martinson was publishing papers saying that by increasing the yield of palm oil, we're going to decrease deforestation, which is the stupidest statement you can imagine. This is total bullshit. And I'm really annoyed that it's published in Nature. This is complete nonsense. Because when you increase the yield of palm oil, you make them more attractive, you create new needs, and it's going to increase deforestation. This is rebound effect applied to plants. Third critique is Goodhart law. Goodhart law, it means that when a measure becomes a target, it ceases to be reliable. So here, for instance, sports competition. So if you really want to get the best score, you're going to do doping, you're going to cheat or whatever, but then it has nothing to do with sport, right? It's just competition. So you lose what you're doing it for. And it's the same in science. There's this famous paper in Park et al. 2023 in Nature, showing that we actually have all of these indicators of performance in science, you know, impact factors, H-index, Shanghai ranking, all this. What it's doing, it's actually pushing us to publish more. And so now this index here, like on the y-axis, it's an index of disruption of the field, if you want. And so what it shows is that in the 50s, we were publishing not that many papers, but they were very disruptive for the field. Now we're publishing a lot of papers that are very incremental. That's Goodhart law applied to science. So you see, we can have a constructive discussion on efficiency. Efficiency can be a problem. And here we are in the era where it's actually mostly a problem. Okay, so what can we do? I have one last one, of course. So when you focus on performance, so really define here as a sum of efficacy and efficiency to reach one's goal with the least amount of means possible, it's always relative. So actually when you are on the performance route, you are actually on the competition route. And in a competition, who wins? It's very simple. In a competition, it's always the most violent who wins. And it does not depend on the system. It's always true. So for instance, a sportsman, for instance, is violent against his own body. It's always true. Huh? So when it's a culture of performance, it's a culture of violence. And we are in that culture. It's a violence against women, against the poorest, basically, and against the ecosystems. So basically, we are turning the world into a gigantic burnout, ecosystem burnout, basically, because we have pushed performance so much. So basically, ecosystems are exhausted by our performance, if you want. Okay, so that's I'm not going to go because this, you know, but that's the first take-home message, is that everything we know from the scientific report on the ecosystems is that the world is going to become much more variable, much more turbulent. We are leaving the era of the mean to enter the era of the standard deviation. That's what happens. So the tendency will trend we will forget about it. Actually, we'll be much more interested in the variation from day 1 to day 2, or month 1 to month 2. Actually, that's what Andini was saying about the 2022 big droughts. Yeah, that's what we should focus on first. It's going to hit us badly in the 21st and 22nd century at least. Okay, so a third way. So since efficiency has many problems, can we derail from efficiency? Actually, so it's just to take a scientific viewpoint in a way. Huh? So if scientists are telling us that the first take-home message from the climate, from the ecosystem, from the economy, from the social, that's going to be much more viable, maybe that's the first question we should ask. Should our projects be driven by this fact that is going to be much more viable? And so that's to me, that's the first question we should ask in the 21st century. And the answer, we have it in front of us, which is what's crazy. That all living beings have been able to manage fluctuations for millions of years. So they have some laws, some principles, some recipes, if you want, to manage fluctuations. So what is the secret that we should get inspiration from? So it's one word, especially robustness. Living beings are robust. So robust means that it's stable despite fluctuation. It's the physics definition of robustness. And when we look at how living beings can be robust, they are robust because they are not performant at first order. Or if I say it differently, living beings are robust before they are performant. We, human societies, are performant before we are robust. It's the opposite. And see here, I've put a number of words here. That's what you find in any living systems, neural network, physiological network, ecosystem networks. So inefficiencies, there's no goal. Darwinian selection, for instance, there's no goal. Heterogeneity, randomness, slowness, redundancy, inconsistency, incompleteness. I mean, all this is things that you find when you dissect the networks, when you have an holistic approach. For instance, redundancy, you just look at the number of leaves there is on a tree, right? This is a redundant system, right? And this is robust. So here you have some examples of randomness in biology. Okay, so this is the first take-home message, and maybe just to give you one example, a classic one is photosynthesis. So we know that photosynthesis, the yield of photosynthesis is extremely low. It's 1%, up to 5% really when you push it in a very few species. Why is it so low? There's this beautiful article from Arpetal in quantum physics showing that actually the main take-home message is that plants need to manage light fluctuations first. And so that's why they are green, for instance. They're not black like solar panels, right? They're green to have less energy because otherwise they would burn. If plants were black, it would be too much, they would be too sensitive to light fluctuation. So you need to absorb red and blue to allow a big space between the two peaks of absorption to avoid burning when there's a sudden burst of light. And so that's why they have such, I mean, one of the reasons why the yield of photosynthesis is so low. There's also Rubisco and all this time. There's a number of reasons, but at the end, you get 1%. So it means that plants are wasting 99% of the solar energy. This is not efficient. Solar panel is much better. So it's not efficient because robustness first. We want to have a system that is circular, able to repair itself, that is adaptable, that is evolvable. That has a cost in terms of performance, right? But it's robust. So this is probably, the light coming from the plant for us. It's giving us the light. So it's goes in the other direction in this case. Okay, so if I take off from the plant analogy, how can we take this message back into society? So what we are experiencing is not an ecological crisis. It's not a social crisis. It's not a geopolitical crisis. It's a cultural crisis at first order. It's a cultural crisis. We've been on the compass of performance for the past 10,000 years. I mean, it's since Neolithic age, since we started to do agriculture, we wanted to increase the efficiency of our crops, of our techniques, of our organizations. And now we are at that point where when we increase performance, actually we destroy our habitat. And it's true everywhere. So now performance really becomes counterproductive. The more performant we are, the less viable humanity becomes. So it's very clear that the world progress will change. So progress so far has been defined mostly by increases in performance. This is not going to be true in the future. and see, I'm using future and not even conditional, because it's just physically impossible. If we increase performance, we're going to channel ourselves into a very small canal, very efficient, especially at a time where the world is becoming much more and more viable. This is a suicide mission. So the future of progress is very simple. You have to change axis. And this is where the cultural moment is. It's a Copernican moment where we're going to change progress. Progress is going to be increase in robustness, because the world is becoming more and more viable, and it's going to become even more and more viable, with variations that humans haven't seen in the past 100,000 years. I mean, we should really see what's going on. So this is big, of course. It's a big change. And you see it's on two axes, because you can't be very performant and very robust. It's physically impossible. When you're very performant, you're on a narrow path, you're very specialized, you're going in one direction. When you're very robust, you diversify, you explore, you experiment. It has a cost in performance. You're polyvalent. Okay, so that's, I mean, here I'm just, taking the scientific fact for what it is, right? It's going to become more viable. To survive, we'll have to be more robust, by definition. So, but is it a little bit utopian? So I'm going to give you an analogy to that I use often to explain how we can shift like this. It's really a big cultural shift. So yeah, I'm taking the example of birds, this flock of birds that are shifting all the time, right? They turn right, they turn left. And apparently when they turn, the birds are not falling down, right? So they manage to shift without damage. So how do they do this? So it's typical of agent-based models. So it's always the periphery, the birds at the periphery that are guiding the group. Because the birds at the periphery are the ones that are exposed to the fluctuations. They're the ones that are seeing the predator coming, right? And so when they see this, or the wind or whatever, so they are sensitive to the fluctuations, they synchronize, and then they contaminate the heart of the system. In the heart of the system, you have birds that are blind to fluctuations. They can't see fluctuations. They just see the neighboring bird. And so what happens is that basically the periphery is seeing the fluctuation, they synchronize, they contaminate the heart, and then the entire system is shifted. So this is true for a flock of birds, it's true for fishes, fish banks, for instance, but it's also true for social systems. Most umpires, they've shifted from an accident happening at the periphery, right? And so this has changed the system. So if you want to see the world shifting from performance to robustness, of course, it's not 100%, it's just a balance, right? So it's a different balance. It's useless to spend time with, Exxon, BP, the European Commission. This is the art of the system. There's nothing, I mean, it's just in the efficiency route. You won't learn much from this. What you want is to go to the periphery, to look at citizens that are already in the fluctuating world, that are already exposed to a lot of fluctuations. What you find in this periphery, in these companies, in these associations, in these small cities, but they've already developed robust protocols. And a really nice message is that actually it's growing, really, it's accelerating now, this shift. And it was not the case 20 years ago. 20 years ago, it was really, Pierre Rabhi in France, really the margin of the margin, right? But now it's really a massive margin that is contaminating the earth. So I'm just going to give you a few examples before I land back to the plant field. Here, for instance, one of my favorite examples, Saint-Martin-d'Auxigny. So you see, they had performance in the 50s, right? So you channel the rivers, you increase the size of the plots, performance, right? But when you do this, here you have a water highway. So when it rains a lot, this water is going very fast to the neighboring cities, and then you have massive flooding in the streets. So you get flooded a few times, and after a while, they decided, well, maybe we should do something. So what they did was this. So they redraw the river, put like some a snaky pattern, if you want. And now when it rains a lot, this river that is slower is flooding the plot, but it's not flooding the city. And so we've decreased performance to increase the robustness of the territory. And what I like about this example as well is that actually this example, which is from a small village at the periphery, we talk about it on TV at prime time on the France 2. So just to show you that the margin are contaminating the heart of the system. So of course, this comes down to exactly what's happening in this room. We see a number of researchers that are moving from intensive agriculture to agroecology. And it's the same in the field. The movement towards agroecology, we can think that it's slow, that it's very minor, that there's not so many people, but actually it's a movement that is not stoppable. just because intensive agriculture is way too expensive and it's too dependent on oil, on fertilizer, on pesticides. This is not going to last in a fluctuating world. It's it's too fragile. It's too fragile. So, and you see that's an inversion. So in the world of intensive agriculture, so post World War II, it's quite recent. We used to use ecosystems to increase production. In the new world, we'll ask how production can feed ecosystems. So it's a very different posture. So that means the farmer is not looking for the best yield. He's looking, or she is looking, for the stable yield over the years. And so to have a stable yield, you also need to maintain the hygrometry of your soil. You need to maintain your insects in your field. If you have mixed varieties, you need to mix your varieties with your neighbors. So this is, the world where you have a lot of interactions. This was a world where you had poor interactions. The highway, you reach your destination, but you don't meet anyone on the way, right? So that's what I tell a lot of young students, right? That the world to come is actually much more interesting than the world we're having, I think. Okay, so at the margin, something else that we see is the all repairable. So this is, you can see everywhere. So like for anything, trousers, jeans, pullover, but also, in agriculture, and electronic, repairable electronic. So all this is blooming, and this is not a coincidence. It's an operational answer to a world that is becoming more and more fluctuating. You just have to think that if China is invading Taiwan next week, China will close the boundaries. And so if you are a company and you depend on one element from China, you're basically economically dead, unless you've developed the repairable in your own territory, and then you can maintain an activity. So that's why most of these companies are developing this. So this is again the margin that are showing us the way. And this here is an example for the plant fields. It's when we use the word decarbonize the economy. So I'm a little bit picky on the words, but decarbonize the economy. This is really it's the wrong word. We don't want to decarbonize the economy. We don't want to burn carbon. So we want to decombustionize, I guess, the economy. We want to stop burning wood, coal, oil, biofuel. If we want to reduce the emission of CO2, we don't want to burn carbon. But we certainly don't want to decarbonize the economy. We want to recarbonize the economy. The bioeconomy, the circular bioeconomy, is based on carbon. We don't want to get rid of carbon. Carbon is the magic atom for life, right? So we want to recarbonize it. So here is an example. So the lithium battery, which is often put as the big solution for climate change. Actually, the socioeconomic and socioecological framework around this is quite toxic when you think about it. And the cobalt, Congo, you heard, right? So we don't want to probably, this is a niche, but this is certainly not a general option. So here you have an example. So Linea, that's a company in Sweden. They found that you can, when you take woods, you extract cellulose to make paper, and instead of burning the remaining lignin, actually you make films, and those films are storing electricity. And so now you can make batteries that are local-based and bio-based, if you want, completely biodegradable. So of course, they're not as performant as the lithium batteries. We can't compare, of course, but for a number of things, and it's research in progress, we can certainly think that we can make locally produced batteries. So of course, there's a legal issue here. We don't want to grow forests to make batteries, right? Of course, so this number one would be ecosystem services. Whatever biomass you produce, it's for ecosystem services. Then it's for food, human food, and then the rest is for biomaterials, right? So it's a question of it's a legal problem. But this is where, the plant science has a lot to bring. The future will be bio-based, will be carbon-based. And so as biologists, as plant biologists, we should really insist on the fact that we want to recarbonize the economy, certainly not decarbonize the economy. Maybe the last example on the margin is the engineers. So here there are many engineers on the plateau. So a lot of them are getting away from schools because they really don't see the interest of increasing the performance, the efficiency of tools. This is to actually increase the exhaustion of resources in the environment. So they are changing. So before the engineers, we asked them to increase performance through distant technical delegation. The new engineers, we ask them to develop robust solutions. And so robust solutions is what? Is techno-diversity. So we want engineers to develop a plan A, a plan B, a plan C, a plan D, and it should be only robust solutions. And the other thing is that we want technical autonomy of citizens. So that comes down to participative research, where you want the citizens to be involved in the repairability, in the evolvability of the solutions. This is much more interesting for engineers. This was actually very lazy engineers. You want just increase performance, right? Not very interesting. This is much more interesting. And you see that the world of robustness is not technophobic. It's the world of performance that is technophobic. Because when you increase performance of technology, actually, when you have very performant technology, it's actually erasing the older technology. It's taking over. That's technophobic. And you increase the distance between the citizens and the technology. It's doubly technophobic. This is technophilic. Yeah. Okay, just to make it very clear. So we see, we switch from smart cities to smart citizens. Again, much more engaging, I think. Okay, so that's the new balance. So we've been like for thousands of years on the compass towards efficiency. And now that we are entering the result of this compass towards efficiency with a very fragile, very vulnerable world, but now we're going to shift to a better balance with robustness. So I'm not saying that we're going to forget about efficiency. There'll still be some niches where we'll increase efficiency. But the main thing is that this will be our main target because the world will become more fluctuating. So what does this mean in terms of plant research? I'm going to give you a few examples. So efficient monoculture, right, very fragile, right? You just need one episode of drought and that's it, you're dead, right? So what do you want to do? Mixed varieties, for instance. Mixed varieties, you have 20 varieties of wheat, for instance, or spelt or whatever, where you have 1/3 that is resistant to drought, 1/3 that is resistant to flooding. So of course you won't have the best yield, but at least you'll have a stable yield. That's a basic strategy for robustness. And there's plenty to do of research on this. Do we really want to make new resistant species, resistant to, for instance, a given virus? So if you do this, actually what you're going to do is that you're going to make a crop that is extremely attractive, that is going to take over the entire market. And then you're going to make even more monoculture that are even more fragile from many sense, socio-economical, ecological framework. So what you want to do, another example, you could instead look at plants that are very hardy, that are very rustic, and see what's the key. Why are they so rustic? What's behind it? So there's a lot of genetics to do on this. There's a lot of research to do on this. Understand hardiness. Here I'm taking the example of a pollard tree, for instance. Pollard trees are supposed to be very resilient. So what's behind this, right? There's lots of research to do on this. Biofuels, keyword, biofuels. So biofuel is really like, an intermediate version, right? So we want to get rid of oil. But if we make biofuels and if we grow crops to make biofuels, but you need fertilizer to grow crops, but you need to go to use oil to put fertilizer. So you basically use oil to make biofuels, to make oil. Honestly, what's the point? So a much better way to look at this is to do true bioeconomy. So here I'm taking the example of the work from Thomas Dehoux in Lyon. So they found that this is what you see here is an epidermis of onion. So if you dry, like just a monolayer of onion cells, and you put them in a microscope, you measure the acoustic signature, you'll see that this mono layer of onion, dry monolayer of onion, has phononic properties. So it's absorbing certain frequencies at, high frequency, gigahertz, so really high. I'm just going to make it short, but in your cell phones, you have some rare earths, which function is to do this, to absorb at high frequency, to have phononic properties. So that's the future. That's the recarbonizing the economy. That's the circular bioeconomy. So one way to go forward is to replace oil and metals by biosourced, and there's a lot of research to do on this. And this is probably more interesting than the biofuels. Precision agriculture, that's another thing, right? Precision agriculture, again, it's a niche industry. If we generalize this, we're going to add more dependencies to farmers. So they already are dependent on fertilizer, on pesticides, on this. We're going to add drones, digital. I mean, do we really want this in a world that is going to be much more viable, even geopolitically speaking? I mean, this is very fragile. We don't want the farmers to be dependent on this, right? So maybe what we prefer is to use in precision agriculture. So instead, that's agroecology, right? It's not very precise. It's very, changing. It's a bit unpredictable. But at least you analyze the network, and this is emerging from the field. So actually, as Jean-Denis said, we don't want to propose the quick and easy solution. We rather want to create the conditions in which the solutions emerge. That's really systems thinking. And so that means that you don't provide the solution. It's like going sideways to make it emerge in a different way. So that's agroecology is all about this. And maybe the last two, of course, the seed company monopoly, very fragile, right? 5 seed company for the entire world. And anyone with a brain would think that that's complete suicide for the planet. So of course, you want to switch to something much more local and with participatory research. And same for this top-down research. And again, you want to balance this. I'm not saying that we should completely erase the past, but it needs to be better balanced, right? We should have much more transdisciplinary research with society. Okay, so just a little, if you want to publish more on this, we have a citizen science format in the quantitative biology, and get in touch if you're interested. So we have I'm part of the editorial board. And that's it. I'm going to stop here if you have questions. There are some books if you want to dig into this robustness route.